It is 8:45 UTC, so I'm going to get started. My name is Wolen. I am a software engineer at TileDB, which makes sense because this is the TileDB tutorial. So the tutorial will be primarily led by Dirk Eddelbuettel, who is a principal software engineer at TileDB. You may know Dirk as the author and maintainer of RCPP and countless other high-impact R packages, but Dirk is also responsible for the TileDB R package, and he's done an amazing amount of work to make sure R has first-class support for users who want to leverage TileDB and R. So I will take over a bit later in the tutorial for one of our use case demonstrations. Until then, I'm going to hang out in the Slack channel and monitor it for questions. So if you have any questions, feel free to post there, and I will interrupt Dirk so we can address them as they come up. But with that, I will send it over to Dirk.
Perfect. Thanks for the intro. Let me turn screen share on. Yes, so Aaron and I are really excited to have the opportunity to present here to you today. We've both been with TileDB for well over a year and working at that. I have focused mostly on this R package, and Aaron looks after bioinformatics applications, particularly VCF. So that'll come up a little later. So with that, this is really the first time that we're talking to the R community about what the TileDB package offers. And I hope you'll all be coming away from this with some understanding of what it can do. We have aimed to keep this somewhat non-technical. We have pointers to more documentation at the end of the slide deck. But by and large, we just want to show you by doing what this is about and what it can do, and keep some of the more technical aspects for a later time, because this is really the initial tutorial. Here's a quick list of topics. The time that we spend will not be even. So among the key topics, I will be talking a little about dense and sparse arrays, as well as the API, the underlying C++ API that we wrap, and I'll get to that in a bit more, and shorter notes on S3, cloud access, and these other points. A few minutes on the application examples. These four are relatively short, and I will then hand over to Aaron, who has a really fantastic and longer genomics example with which we basically conclude, and then we'll wrap up. It is, of course, a little challenging to do this via Zoom without being in the same room as you. I've been giving tutorials at USA for maybe a decade, and it's just lovely to have eye contact. We don't have that here, but at least we have 4 eyes and 4 hands. And I think the general gist is that you're asked to put questions into the Slack channel rather than the chat room here, if I have that right. And between Aaron and myself, whoever is not talking, we'll try to keep an eye on the questions, and we will try to break frequently enough so that we can address questions as they arise. I hope that's good for everybody. So TileDB, here's a screenshot of the website, makes a very broad claim that we're aiming to make data management universal. There's one storage format, the TileDB array, which works particularly well for dense and sparse arrays, and we will show you a couple of these usage examples. And multidimensional, particularly sparse arrays, fit, for example, data frames really, really well. These data frames are the bread and butter for R. That works very well, and obviously it also works with numeric arrays, matrices, and all of that. And it's serverless in the sense that something like SQLite or DuckDB is serverless. It really is an API, a file access layer that's provided as a library to which multiple tools can connect. And we're talking today about the connection from R and to R. And that went in the email to you. We put these slides as well as the example programs that I'm going over, or example snippets, into a little R package that sits at this repo at GitHub. And in the email that went out, we only gave half the repo. So if you run install packages, but don't have all packages that this package requires on installed. It cannot resolve to the other packages. So the better form from installer packages is to extend repos beyond just CRAN and or bioconductor and other repos that you have. Add our little ad hoc repo, and then the TileDB package comes in. When you then do library on the installed package, it will just show you a little welcome message and, for example, tell you where the examples directory are. That's just the per package example directory. And with that, maybe I'll do a first pivot to a fresh session. So I just do this in Emacs here rather than from and this is installed on my machine, and then it greets me that, yes, in my local path, in the examples directory, we'll see the scripts. And I just cheated to keep the path shorter and made this a soft link, but you should have all these examples in the directory, as well as, nope, didn't mean to do that, as well as a function slides that then finds the PDF and brings it up. So you don't even have to type the path out. So that we updated a few times and updated the package still after we first emailed you all. So we're internally now at version 0.13 of this package, but it didn't really matter. The slide deck as emailed yesterday was pretty current. We are also on Slack at the conference in channel tutorial TileDB, and Aaron and I are trying to keep an eye on that and see if you have questions in here. And I just noticed that someone didn't want to scroll right. Right, perfect. So let me just type real quick. So questions here. So with that, and a quick eye contact with Aaron, who I can see over there. Does anybody have questions so far, or are we mostly good and set up? Beautiful. So the first thing that I'm just going to show is a really simple and quick example, and we will go over each and every of the underlying commands in more detail later. So with that, let me hop out of this, get back in here, and this is the exact same code that's on the slide. I do not need to execute this first line because TileDB itself is installed for me. So I can just say TileDB, and I had in this R session already done it a second before. When you first load TileDB, it tells you what the version is, and 0.94 is what is currently on CRAN, and it then tells you what version of the underlying C++ library giving the TileDB functionality is loaded as well. In my case, that's 2.4.0. because I work here, so I tend to work against the development version. The release version is 2.3.1, and nothing that we're doing today should affect any differences between these. A data set we'll be using left, right, and center because it's simple and easily understood is Parma penguins, which I'm just loading. And then because TileDB arrays, unless you go to the cloud, really make use of directories and create from a top level directory, the array name, the array descriptor, the array URI, a set of files below it. So I'll just go here to temp because I'm now creating a first array in a temp directory, sort of just a throw off. And a helper function, a high level function that we've written for the R package is just called fromDataFrame. And it takes an object, here the penguins data frame from the well-known penguins example, and will write it to the address given. There are other options, we'll see them. So if I first execute this, and that happens. And now I will just do, because I had done it there before. So when you ask TileDB to create a new array, the creation of the array is the initial write, and that will error out just when you try to write to something initially and the file already exists. You can later open an existing array and append to it, but the initial creation assumes ex ante that there's no overwrite or delete operation going on, but that it creates it the very first time. So when that little boundary condition of does the directory already exist or not is taken care of, all it takes is take an R object and a location, and you write the directory. We can look at what's written there, but I've never really poked into this, and I'm a developer here. This is mostly opaque. The view that we have of data is that we're presenting the storage not as a format specification that many competing implementations could provide, maybe get right or in slightly different incantations. For us, the code is a specification. The format that TileDB presents is presented in one API, and that API can be connected directly from C++, or R, or Python, or Java, or SQL databases and others. And it then, similar to other database systems, if you ever looked under the hood, it writes in a directory where the writing begin and end timestamps are encoded in seconds since the epoch, as well as the UUID handle. So this one is just where the files are. This is a 0-byte OK flag, log, and meta and schema are directories for additional data. And then in the directory itself are files with one file per column of the data frame, plus some other bits and pieces. If you have columns that have null or nar flags, there's a fidelity counter, but none of that we really need. I just showed it because one wonders, okay, we write to that directory, what then happens? What really matters is that we can treat this URI here, penguins, as the source of a TileDB array, and the other way around, from the written array back into storage. The catch-all function that we will use a lot is TileDB array, which will open either dense or sparse and recognize it from the schema. And here I used 2 additional attributes, one saying that I want it as a data frame, otherwise I'll get a list, and we'll show that later. And extended false just suppresses a display of implicit row names when we're writing and do not give row names explicitly. So then that is being added. The handle itself for the TileDB array is an S4 class with various attributes. We'll hit a few of those. Some of them are Boolean toggles, so we want it this way or that way. The sDataFrame that I then used is 1, and that sets it to true here. Once we have the array opened, I can just assign with square bracket operators, extract me the array, and I have a data frame back. And this is now essentially the same as the penguins data frame that goes in, including transparent treatment of missing values, different variable types, with only small differences to R. So for example, we haven't yet done anything about representing factors, because factors are really an R specialty, and we take a sort of slightly broader view in the TileDB representation that what we write down also must make sense for Python and other languages, and they don't really deal with factors. So if you write something in as factor, you may get it back as a character variable, but as things have evolved, that's more or less the view that R takes these days too when you read from CSV. I see one first question coming up here by Brigitte saying, why use an array instead of a data frame? That is mostly just lingo, if you wish. For TileDB, everything is an array, and what we would have in R as a data frame gets stored in array. There's just no TileDB accessor function, TileDB underscore data frame. We'll see a bit more on that. The ability to store as a TileDB array extends to numeric arrays as well as to data frames. I hope that that answers that question. Okay, so that was the very first introductory example. Here's a follow slide on what we just saw when we access the array unconstrained, no additional selection on rows or columns. We get a data frame back of all the observations of all the variables, because we are asked to have it returned as a data frame. What we will look into a little closer in the coming minutes then is differences between dense and sparse arrays, and when we might want the one or the other, how to operate with indices, a feature that requires sparse rather than dense arrays. But we won't really talk about some of the available tuning options, the tile extend, the layout today. That's sort of for a second tutorial. They can affect performance in the large. It wouldn't matter for the penguins, but when you write gigabytes, which we'll show, or how to access arrays of that size, it matters a little, but it's a slightly more advanced use. All right, so let me start by dense arrays, because dense arrays are conceptually simple, and dense arrays historically is also where TileDB started. Dense arrays tend to be a bit more limited in the sense that they require the same variable for the indices or rows, columns, or third and fourth indices, so you cannot mix, as we will do later with sparse. So here we have the very first example, quick start dense, that starts in the TileDB documentation at the very top in a C or C++ example, and some Python examples. And here I'm showing you, and we'll come back to that a little bit later again, basically how we would do these operations with more atomic TileDB commands that correspond more directly to the underlying API. So when we ultimately want to write an array, we first have to create a schema. A schema is a combination of a domain and attributes. Domain is really important because that's what organizes the array. So here in the simple example, we're simply saying we're going to have rows and columns ranging from 1 to 4 with max values of 4, and they're both being ints. And here we're just having 2 of those, so a simple vector that assigns to DOM. We're then using DOM, the domain, in the creation of the schema, where we're saying we're going to have a single attribute that would be in a data frame, a value column that's not an index column. In this case, very boring. Also in 32, and we will refer to the attribute column just as A. That makes a complete schema. And just how we had the helper function from data frame that really generalizes and uses the same scheme that these underlying ones have. A TileDB array is then created by where do we want to create it, what you write, and what schema. The schemas can also be queried. Once we have this created, and in this case, remember, we created a 4x4, we can write the array by creating a 4x4 matrix, or an array rather, and assign to it. And with that, let me pivot back to the corresponding example for that, because it is actually nicer to show that directly in the code. So that creates the DOM, that creates the schema. At that point, I can actually look straight at the schema variable, which is really just a display of meta information, a little bit of the header information. You know, did we select column or row order? Call is default because R is the same. A couple of other things, are there compression options? Things that we don't really need to look into too much, but we said 2 dimensions. Here, the 2 dimensions showing the 2 names, and there's already the attribute that's in there, quick start dense. Now I can write. Again, I could look into that directory and see the underlying file. The data that I'm trying to write here is a 4x4 array, and then I can just write it in. First open the array, and then do a write assignment with the square bracket operator, and I can get the same thing back. And when I say nothing, if I just open it and query the array, by default, I get very R default-ish a list of the columns. For a dense array, and if I don't say anything else, I get rows as well as columns and the attribute. However, if I say I'd rather have a data frame and run that, then I do as asked, get a data frame back, which is here printed the proper way with the row names and class of what comes back is just a data frame, nothing fancy. Because you have a data frame, you can then go down the pipeline and do other things with it. I often use data tables. We also do tibbles, everything that derives from a data frame. Similarly, because this was a 2x2 array, a 4x4 two-dimensional array, which is also a matrix. In this case, we can also say, give us a matrix. We have some application cases where people really want matrices, so that's why we put that option in. And then more recently, someone actually really wanted three-dimensional arrays, and it turned out that I had been focusing too much on the matrix special case and wasn't treating the dimensions in excess of 2 all that well. So that was a quick bug fix not that long ago, and version 094 has that. So if you write a 5-dimensional array and say as array true, you would get your 5 dimensions back. So that was first half of dense arrays. I showed all these examples for the generic TileDB array accessor function and the different qualifications for the return type. But we don't have to just stick numbers into dense arrays. We can also write data frames in dense arrays. So here is a dense array data frame example. So let me just go over the code in the second half from that file. For the URI here, I'm just saying temp file. That's a really easy trick, of course, for tests and demos, because temp file is a new directory and you can't have a problem writing this. Now I'm just doing the same, but I'm writing the raw penguins dataset rather than the cleaned dataset. And then look at this again, and it comes back basically the same as it was before. Characters, numbers, values, and what have you. Sort of one of the big differences really between dense and sparse arrays is that the underlying storage for dense arrays really requires a cell to be present at every intersection of the indices. So for a 2-dimensional by rows and columns, no holes. Really how we think of a data frame, because when we print it, we also see it printed without holes, contiguous. So it's contiguous vectors, and it's good for some cases, but it is a bit more restrictive for really powerful applications. So that's why we'll be pivoting a little more to sparse and work a little bit more for sparse. But there are cases where dense is better, and it depends a little, and it's hard to make a sweeping statement that one truly dominates the other. It really depends a little on your problem domain. So that was dense. That was my first sort of subsegment. Any other questions? I see that Brigitte and Aaron were busy over on the chat. Aaron, any hand wave? Anything we need to break for?
No, I don't think so. We had 1 or 2 questions in the Slack channel, but you addressed the first one, and the second one's about whether you can store different data types in a single array.
Yes, I mentioned that in passing, and maybe I ate my words or was too quick. So the big constraint on dense arrays is that the rows and columns have to be the same type. When we take a data frame like penguins and write it in a dense array, which is the default when you don't say sparse equal true, we're actually cheating and writing it as a 1-dimensional dense array, because there's only the implicit index of the row names. And every data frame has row names, row numbers. We can always create an index by just numbering down from 1 to the row dimension to dims 1. And that's basically what we're doing here. And that allows a dense array, dense index, just row indices, to have different columns of different types, mapping the data frame capability that we could otherwise not have, could not be matching. So yes, very much so. We can have different data types in the different columns, just not in the indices, which ultimately gets limiting, because once you have really large data frames, you want to index on more things than just the numbers. And that's where sparse enters. And coincidentally, that's what we're coming to now. So speaking of which, it's a little hard for us to keep track of who's there and who's not here, but I can sort of hand wave because I recognize a few names popping up. And so this is a shout out to Martin Mechler, because here's a sparse matrix example straight up from the matrix package, motivating what we can do with sparse, because the first way to show that, of course, is by actually creating a sparse hold on, this is annoying. Let me just take this one out because I don't need it anymore. And then it will no longer ask which R session I want because I only have one. So matrix package loaded, temp file set seed, so that's reproducible. And I think this is literally a numeric sparse matrix that I used in another package of mine when I wanted to work with sparse matrices. So this is 100% matrix and nothing TileDB. So I have a sparse matrix here of type DGT. There are different types that the matrix package supports. The most common one is DGC, but it has a more complicated indexing scheme. And what we're using here is DGT because it corresponds more closely to first index, second index, value. And we'll see that in just a second. So basically what's in the internal S4 representation of a DGT matrix maps the TileDB representation naturally. So that's actually pretty cool. And just how we had a fromDataFrame generator, I then created a fromSparse matrix generator. And so this one just writes the R object at the given URI. Here again, a temp file to be simple. Check opens the array again to read it. And so these two lines give us a round turn check. And you now see that the CHK matrix that I read back is exactly the same and indistinguishable, I think. So I can pass that through all equal to the one that we wrote in. So what's different now? Well, sparse matrices are very powerful in many big data applications, just because we often have data sets naturally with sparsity. You can have matrices where not every cell is presented. Here I had one where in 8 by 20, 160 cells, I filled just 15, so just under 10%. And as we'll see then in the next example, it works really well also with data frame examples. The main advantage by enabling sparse equal true in our bread and butter function fromDataFrame is that I can now also designate some indices. So here for the penguins, I'm saying, let's use species and year. And I then should add that they will have slightly different treatment within TileDB. Species was a character variable. For character variables, we basically say that the domain is from null to null because you can't really meaningfully enumerate the set of all possible characters. So they're basically unspecified. That has one great advantage, because once you write a sparse matrix where a index dimension is not limited, you can immediately append to it because you can never write past the predecate maximum value. However, if I did column index species and year and did not say year, say 2000 to 2021, I would not be able to write beyond the penguins data set, which, if memory serves me right, has examples from 3 years, 2007, 8, and 9. And a pretty text example that I had was just saying, okay, let's just set one up, but put a wider range on the years so that we can append to the data. We'll have a fuller example on that. And so if I don't say anything else, the data frame comes back the way it came in. It may be slightly rearranged relative to the R original, not dissimilar to how data table, if you know that, works when you key some variables. Because once you give an index on a particular column, it will use that key by default and sort by those values. So the I've forgotten, well, actually I can do that now. I forgot what head on penguins was, but for starters, the order is different, and we're lucky here because it also started with Eddelbuettel and in 2007, so it's the same year. So we get the 2007 vintage before the 2008 and 2009. But because we designated two columns as indices, they come back as the first two columns. So the column order is different from what we originally had. So you can't do an all equal there, but you can do an all equal on each of the columns. What we can then do when we have a data frame with an index is that we can open it again. So I've shown you new DF and nothing had changed here, and the dim of, the unconstrained is the same as the original data, 344 by 2. But the nice thing now is when we have indices, we can actually use them. And TileDB is a lot about performance with really large data that may sit somewhere else. So I chose to represent the indexing by columns as a free function where we're selecting range constraints on the array objects that we opened. So select ranges will modify the X object. X is our TileDB array with the slots, and selected ranges, as you can see, when it's not set, we'll just say none. But this convention here is that we can submit a list with as many elements as there are dimensions, named or unnamed. If they're unnamed, they just have to be in the same order. If they're named, then you can have subsets of dimensions that you constrain. Here I have set 2 in the example and I submit to, and I'm basically saying, okay, I want the year to go from 2007 to 2008, boundaries included, but for species, I only want Gen 2. So from Gen 2 to Gen 2, which amounts to an equality constraint. And when I then look at that, my 344 is down to 80 because I expressed a selection constraint. And that's pretty cool, because we will see examples later where the URI is not a temp file, but something remote. And by selecting from where we operate what subset we want, we're just transmitting the request for the subset to the backend, and only selected data will come back. That matters a lot for our remote and really large scale operation. A more recent addition to our arsenal is that we can select not only on the dimensions, but now also on the attributes. That is still a little more restricted. Certain things work, other things don't, but it works already very well on numeric conditions. So in the more bare bones API representation, I'm saying, let me initialize a query condition on one of the attributes. And here I'm selecting body mass in grams with a cutoff value of 6,000. This column is of int32, which we always have to specify, and my condition will be greater or equal. And when I do that, and basically assign this query condition to the query condition accessor as for accessor to the array object. If we, for example, if I now looked at X, we have selected ranges as well as a query condition, that's set, and query that. My selection from 80 is down further and just down to now 3 rows, because I had the initial index selection 2007 or 2008 for species only Gen 2, but I also wanted my body mass index to be over 6,000. And that's pretty neat. That's in the CRAN version. What I have here, and which is in GitHub, but not yet on CRAN, because we only release every couple of weeks. So this is just something that just got added in the last week or two after the CRAN release. We now do a little bit of clever parsing on our expression trees. I'm just making this a little richer than the one that we had. So we see here that with the current constraint is greater than 6,000, I get 3 back. Oh yes, sorry, I'm riffing. It's the end that we translate to, but the R expression has an ampersand. See, that's what I get for changing the code on the fly. And when we do this now and do a dim on it, we will have 2 rows. Yay.
Dirk, we had 2 questions in the channel.
Yep.
Someone asked about your selected range. Why did you use cbind on the same column twice?
Oh yeah, sorry. Very good. Excellent question. Sorry. I'm I was so performance focused here, and I think we will have examples on that later. But think about a really large data frame of 1 million rows, and it's indexed by years or dates. And say you want multiple chunks. Say you have something about all birth years in the 20th century. And you hypothesize, you're doing social science, and you hypothesize that people who are born in the first year of a decade have different outcomes. So you want everybody born in 1900, 1910, 1920, 1930, and so on. For that, you would use the C-bind trick, because the full specification of what I'm sending in here is actually a matrix. And using a C-bind this way is just a really quick way to allocate a matrix, which is sort of one quicker than I find. Than doing it this way, but they are equivalent, because what selected ranges, I'm riffing without a safety net. Will I blow up? Okay, I got the same one. So I'm basically just using this format because it's quicker than this format, particularly when you only use 1 or 2 values. And one thing that I haven't done, because nobody has asked, but probably should, is for the special case of the equality. If you only submit 1, it could trivially expand, of course, also to 2. But we haven't done that yet, just to keep it simpler. But for selected ranges, the condition really is a list of matrices, and the matrix can express an inequality constraint on every row of the matrix. I hope that helps.
Yeah, another good question. Someone asked for a clarification about the difference between a query condition and selected range.
Yes, once on dimensions and once on attributes. We especially the core team, think very much about the bare bones functionality in the system and not the high level ones. We discussed that a little already, that maybe there should be more seamless between the two of them, but because internally dimensions and attributes are treated differently, the selection on actual index dimension is different than the selection from attributes. So you basically have to remember how you wrote out your array and what type it is, which the schema function gives you back. It will tell you, oh, this was a dimension, or this was an attribute, and then correspond accordingly. Yes, and the TileDB query condition in it is a little similar to a SQL statement, because that's basically what we're doing there. We're essentially just having relative operations of column type, value, operator, as well as booleans between them. As of right now, the only boolean that's supported is actually an AND. The OR isn't there yet, but that's planned. That's in the underlying API. And then you just generally have a column, so an attribute, an operator, and a value. And we can combine and nest them. Just how I had an AND here, we can do that with more complicated expressions. And I think, for example, we currently can't span expressions that span 2 columns or things like that. So that's relatively new, and we quite like it because it's richer than just the selected ranges feature that we had for a couple of months, which is very good, but it basically forces you to think ahead. Will I want to query on this or that column and make that column an index column? And once it's an index column, you can no longer constrain it. And with the query conditions, you now can. So we're quite excited about that. And for the question of if one wanted more, so for example, one wanted Eddelbuettel in Gen 2, you would here say species Eddelbuettel, C-bind Eddelbuettel and then Gen 2, because then you would get all species greater than Eddelbuettel and less than Gen 2. And I've forgotten what the third one was, whether it was in the middle or not, but that's basically what's happening. So that was the quick overview on Sparse. We'll come back to a bit more of that in the application examples. All good. I see no pressing questions, so I'll move on a little. So yeah, this is a bit more here on the query condition thing again. So what column, what cutoff value, what type. It's a little restrictive because, you know, when we run this piece of code, we actually don't have a connection to the array, so we can't yet infer the type. So we'll have to work on that a little. So that's when you actually want a float value, you have to trick a little and put a dot in there. I have an example for that later. And then if you install TileDB from GitHub repo, you get pass query condition, and otherwise that should hopefully be on CRAN soon. Because we're in pretty good standing at CRAN, have no open errors, so when we upload something, it could be PS in short time. Oh yes, and the other thing, of course, that I hadn't shown, but is here, the last one is, we had done everything so far on row conditions, but you can also open a TileDB array representing a data frame by saying, only give me, hold on, what this is, oh, new df, not df, my bad. So this is basically, this is like dplyer's filter, select rather, filter. So you say which columns you want as opposed to which rows. The two of them, of course, can be combined, and you'll always get the index columns back as well. Hope that makes sense. And that way we can, you know, subset horizontally and vertically. And I think that's what I had for sparse arrays. Yes, and the reason I showed the Gen 2 and the Penguins example with the years is for certain problem domains, you do want incremental writes and appends to your arrays. And for that, you have to just plan ahead and set the range values on your domains large enough. So for example, with geospatial data, we sometimes set, which are encoded numeric, not character, so they don't have the null string, the empty string. So for the numerics, we have done things like just setting them to float min and float max. So then no matter what additional values you may submit can get written to it, but then you don't yet have a logical constraint in it that, you know, that you want to make sure that the XY location is on your continent or planet or what have you. But that's basically how that works. So for incremental writes, make sure you don't limit yourself from the domains. And if you just write from a data frame with the helper function from data frame and don't specify domain values, the function doesn't know any better and can't read your mind and will set as a domain the values observed in the data frame. So then you can always write in between, but not beyond in terms of values. I hope that makes sense. And yeah, and one other important aspect is individual writes are all immutable, which means they don't interact at all, are independent, and hence highly parallelizable. So that's really neat. So if you have really large data examples, you don't have to write one part after another part after another part, no, wait for completion. With additional, with sufficient compute resources, you can spray the writes at an array at the beginning. Question by Paula about what function just gives you the index.
If you could return the schema, right? You could print the schema of your array, and then use the dimensions function would return just the dimensions for the array.
It's a complicated question in the sense that suppose you have a really, really large data set written on the cloud somewhere far away. And if you just want the index, we're performance obsessed. So we would not, we cannot just give you the index back because that's already expensive. You actually have to traverse all the tiles to pick up all the index values. What we do offer you happily always is cheap operations. So what we have for every index are the bounding values. We can give you immediately on the index back the minimum and the max value, which is sort of the outer hull. But if you wanted to query them, that's expensive. So then one would have to bite that and actually do a select query with maybe just one attribute and get them back that way. But it's good question, good suggestion. I have a few more slides here, just with a few words on fromDataFrame and TileDB array, sort of the bread and butter function that I've seen. So fromDataFrame is really what I use day in, day out for test example and checking things, because data frames are just such a bread and butter data structure in R that we want to take it and write it to an array. And we can write dense, the default, as well as sparse by setting it. When indices are not given, it will add ad hoc row indices in either dense or sparse cases. But once you pick a sparse array representation by setting the toggle when you write it, you can have multiple index columns, and these can be in numeric or character. So you can really index the way you index in a data frame, as we've seen in the penguins example where we were indexing on the species as well as the year. By default, it writes compressed, so it's efficient. And we can set different array attributes and parameters still to the function, and we can use append mode if we have high enough domain values that I alluded to, and which I'll show again a little later. In the other direction, TileDB array is our main reader function. So in the first versions of the TileDB package, we had different accessors for dense and for sparse. It was similarly done in some of the other APIs, but we internally normalized a few things in the API to unify things. So now we're just using the same functions to access, whether it's dense or sparse. So you'll always just say TileDB array, and when you're reading it, it's written. It will tell you whether it's sparse or dense. So you don't have to say it on the read. In the R package helper, I put some niceties in that I showed you earlier on a slide to return a data frame, a matrix, or an array. And when considered by rows as well as by columns. Row ranges via the dimension constraint as well as the query conditions that got added recently, and we can select what columns can return. That's what I had on the high-level functions.
We had a good question in the channel about checking for duplicates in the index. Are duplicates allowed in arrays?
Yes, because that's a change that came because the customer wanted it for something. I think that came initially from the Python API and some use with pandas. I can't remember. So that's another flag that I hadn't mentioned. And I think it just inherits from what one sets for sparse. So when you say sparse, it also allows for dupes because we can, whereas in a dense array you can't. I mean, the row indices have to be incremental. So duplicates are absolutely allowed in the sparse case. We really think of TileDB as a unifying API implemented at the C++ layer for the different applications, languages, implementations that can consume it. So what matters to us a lot is that the underlying API functions are present in the different accessor package. So underneath, the R package really one-to-one maps each of the C++ functions. So instead of using the highly compact expressive R functions that I've shown you, one can also do it more atomistically, more bare bones, which one sometimes needs for more complicated cases or cases that I haven't yet covered in the high-level functions. So this basically is the long-form version of the quick start dense first example that we started with quick start dense. So again, a vector of 2 dimension for the dims, one attribute, create a schema from the 2 dims and the attributes, create the array, set up data, open the array for writing. We haven't said much about row or col major because the changes in behavior to us are not that meaningful at our level for the intro tutorial, so just take that as it is. But then the way data gets written for the queries when you do it by hand is that you essentially take each vector, here the data vector, and assign it to a particular buffer, as many buffers as you have columns in the data set that you're writing. You submit the query, you finalize the query, and you check the query. And that works very well if you want to or need to write it that way, though of course we don't recommend it because the higher level functions are more expressive. As you will see when you're eagle-eyed, this is a sequence of operations that all have the same common first data type, the query. So it lends itself to piping if that floats your boat. So we can run the same example in R410. So I guess that was the one example to someone asking earlier whether R4.0 will be good enough. You couldn't run this example, it is, but you can just drop in the Magritta pipe and then it works the same way. So that's the same. So basically everything that's in the API can be accessed directly. And if you go to our package down documentation for the package, you see a really long list of functions because there is so much, but it can be a little overwhelming, which is why fromDataFrame for writing and TileDB Array for access can be so helpful. Here's another example that one sometimes needs. We currently don't have a high-level wrapper for metadata consolidation. Basically, every write that you do writes to the array. You can append to an array, write multiple times, and when you read back and having consolidated from multiple writes, then it has to, by hand, pass the metadata together, and you can help it by consolidating that first after a sequence of writes. And you would do that by calling array consolidate. And here we show that when you asked for configuration, you get a config object back, which in R's case is just it's like a hash map. It's a named vector, and you can set all the elements by their name. So here we're just saying, okay, read in parallel, write in parallel. On the virtual file system abstraction, also use multiple threads. Consolidate me the fragment metadata. Then we use all these changes and create a new context object. And the context object is a hidden global that all the functions access, but if you don't give an explicit context argument, it'll pick up the one that sits in the environment of the package. So this is sort of basically hidden paths from here to there, and then it runs with the context object and picks up the set configuration and consolidates. So that's the second example on what to do with the low-level API. All right. Any other questions? Paula's question, yeah, not quite. Let me go back to an example. Oops, I went too far. So, of course, the example that you had was, is it subsumed in TileDB query condition? Not really. What happens here is we're just opening an array, selecting ranges or setting query condition, and doing all of this on the array object, the S4 container, and in the behavior implemented by the accessor, all these things get set up. So something like TileDB query set, making the different buffers ready, submit the query, finalize the query. All that one happens sort of in this one line because the accessor is high level. So I said from DataFrame and TileDB Array. What I also have said, should have said, is that TileDB Array then gives us the square bracket read and write operators, and those also abstract a lot of the low-level stuff away, so that you don't have to do it by hand. And they basically set this up in the query setup before the query submission and query resolution. Hope that answers that. Great. So first example is S3, because everybody's excited, of course, on the cloud and may already be working on the cloud. And TileDB has been essentially cloud native since day one. When you build TileDB or install the TileDB package, it comes with the features to use Amazon S3, as well as Google Cloud Storage and Azure. I mostly work with AWS. So I commented this out here and showed on this slide as well. When you want to use a particular bucket in your namespace, you need your secret access key and key ID. And if those sit either in the TileDB config object or as environment variables in your normal session, your bash cell, or where you set environment variables on Windows, then you can access that way. And that I can show you, and that's just one change we made in the 24 hours between the first cut of the slides and this version of the slides, because this one, and now you see that, you know, in Emacs, my little clock is spinning, because that wasn't instantaneous, because it didn't go to my local disk, it actually went to the cloud. And I think that's Amazon Data Center East. Oops, that's not what I wanted. Sorry, that's still just that's the array object that I wanted to show. This is what I wanted to set up, and then we can query. And then again, it takes a little longer than from the local disk, but not very much longer. And this example, you should be able to run as well, because we set up 2 buckets. Aaron will show the other one later, a much larger one, within USA 2021 within TileDB conferences. And this one, while it is on AWS, is a public bucket. So I think you get to that one even without a setup AWS ID and key. All it needs is our software's ability to deparse an S3 URL. And that is actually quite magic, because I used all the other examples with URIs that were in my temp directory or a temp file, and just by prefixing it with the cloud accessor, as well as buckets that you have read access to, either public ones or the ones set up by your research group or company, you can get to the cloud immediately. And everything else that we had said about selecting rows, selecting calling, subsections works transparently from the cloud. So that one's nice. Another one that's useful, and where we have had support now for a couple of months, and I'm just going to maybe show that first from the code example, is that we are able to support the Arrow memory format, because Arrow, so now I have to load the Arrow package. Arrow allows you to construct Arrow objects without actually hard linking to it. So now I just in-R loaded the Arrow package. And here I created a really trivial small integer 8-byte vector of 3 values, just the sequence. So this now is an Arrow object. And we can use and do use a feature of the Arrow package that allows straight up C-level interface. If you're a C programmer, it's a bit like accessing via pointers. So you basically grab a pointer of the data and a pointer of the data. There's a little bit of clever trickery going on here, because the pointers are really memory pointers. What R sees is just a double, but what it does behind the scenes with it is the magic. And so these two allocate them, and then we say, because memory got allocated, you should be a good citizen and actually give it back to the system. So on exit, we free it. And then we use an exporter function that exists in the Arrow package and just hand it the pointer for the data and the schema in the types that Arrow can use. And now we've exported from Arrow. So the export is in Arrow in Arrow's viewpoint. So now we exported from Arrow to TileDB, and we can do the opposite by using these opaque elements AA and AS, which I couldn't actually print. They're still just these vectors, but I can use the Arrow function, import me an array, single column from AA and AS from Arrow, and create me a new object with that. And now I've recreated new VAC, and it's indistinguishable from the old VAC. It's still an int8 with the same payload. So that's pretty nifty. It's still relatively bare bones, because we're currently doing that column by column, but we will be doing more there. And the nice thing really is that it keeps the deployment and the build cleanly separated. You just use that with the TileDB package, which isn't linked or built against Arrow in a hard fashion, and the Arrow package, and all they use is a C API that is provided by the Arrow API. So that's how Array internally also does some things, and we're leaning on that. So that's quite useful. And the slides just basically show the same example in code that I had there with setup. Two other features that are useful, and one that I'll show quickly, is we had said that, oops, that's time series, not time travel, that's what I wanted. We had said that the writes are immutable and separate, and we can also do several of them. So here I'm just going to do something really simple. I set up this very boring data frame key and value 1 to 10, 1 to 10. We'll just see the difference in a second. And I'm just going to write it to a data frame index on key, say sparse equal true, and I need dubs in here. And so then I store my current time after I've written that. And now I'm just going to wait 1 minute. I could have done the example with 5 seconds or just 30 seconds, but 1 minute is a bit more explicit, makes us see the difference more explicitly. And then we're just going to open the array again. You see that on the line where my cursor currently is, and override the value column by just adding 100 to the existing values and write that one back. So our data frame D had key and value 1 to 10, 1 to 10, but then the value column, we will just increment by 100. This should be finished now any second. There we go. That felt very long. So now we'll open it again, write and take the time. And once we open it and read what was just written the second time, we see that we have the new values. The 100 got added, so that's what's currently in the array. We opened the array, we read from it unconstrained, and we see it's 100 to 110. But we can use the same bread and butter function to open by saying, really, I wanted it at the, hold on, let me just show that too, because we've looked, we've looked at the directory for the other one before. Now we had 2 writes. So you see that I have 2 directories with data with 2 different timestamps. And that's what happens behind the scenes. Each write is immutable. But when we then come back and read it and tell TileDB that we actually want to read at a particular timestamp, the earlier timestamp, and then look at that data, we in fact get the earlier values back, 1 to 10, 1 to 10. But the other ones are still there. If I want to read it at a different time point, here I'm just saying more current, which would be the same as unconstrained. Then I get the updated values, the overwritten values back. So that's a little bit like Git, keeping track of things and allowing you to come back to older versions, and can be really useful for tracing and auditing purposes. So that's time travel. And a similar feature, just an additional add-on. So this is just the slides of what I just showed. Works with encryption. So rather than writing the data straight up to disk, we can also pass them through an AES 256 encryption filter. And when you then read it back with the encryption key, you get the exact same data back. So let me show that example real quick. So again, I'm setting up a boring domain and schema and set up an encryption key. I've forgotten the exact specification for that, but AES 256 has some requirements for what actually is a valid key. So you can't just write the brown fox or ABC. It has to be a certain length to give a minimum entropy. And this one is boring, but it happens to qualify. And now I can just say, yep, write me this schema with this encoded key. And I'm going low-level function here. I'm doing an array create. Then I open it with the key, write to it. And if I then wanted to just open it without the encryption key, TileDB would tell me, no, this doesn't work. This is encrypted with AES 256, but you haven't given a key because the default is no encryption. That doesn't work. But if on the read I supply the encryption key, all is well, and I get my data back. So time travel to get access to different writes, as well as encryptions are additional features that may be useful for particular use cases. Yeah, yes, the question on the is the data saved twice? I guess, apologies for that. I may have been, again, too quick. So the data really is written twice. So that would be redundant and wasteful, which you can overcome when you consolidate the data. I think time travel goes away after you consolidate, but you definitely have the option of not consolidating if you want to have the different writes persist and retain the ability to travel back in time. We hope that with the example package that we gave you guys, and the TileDB package being on CRAN, you have an ability to experiment a little and follow with the examples. So in a similar vein, I have a set of examples that illustrate other aspects, and I think for one of them I will have to be pivoting to AWS. All right, sorry for that, and we're back, and I now have 2 prompts on AWS, which we'll need in just a minute, but that's the second or third example. So the first one is a pretty interesting one too, and requires a little bit of setup that I have both on my machine and on AWS, because it involves SQL. This is quite powerful because TileDB, as we said, really is a storage layer as opposed to a compute layer. But a storage layer can cooperate nicely with some databases that have plugins for storage levels. One of these is MariaDB. And so MariaDB is the newer version or the variant of MySQL, quite popular, quite extensible. It just so happens that when you compile, when you install MariaDB with plugin extensions, the plugins have to be compiled exactly consistently with how the server itself is compiled. So if you want to stick TileDB into MariaDB, so you have to compile the TileDB plugin the same way as MariaDB, the server was compiled, which also means you have to be the TileDB components there. So you really have 3 compilation requirements. That makes it a little harder to just have a MariaDB plugin, say, for Conda or Ubuntu or something like that, because we don't really have control over how MariaDB is built there. So we have to sort of do it ourselves, or you can do it yourself, but then you have to have all components there for building all of these parts by hand. It's all open source. It's not hard. It's just a little bit of work, but it's easy to avoid the work because you can just rely on Docker. And that's what I'm going to show you. So we provide at TileDB a free MariaDB enabled container that also has R in there. So you can just pull that. And with that, we can then work quite easily. And that really is 3 steps. And that may look like a foreign language to you if you've never worked with Docker. I, like a lot of other people, really quite like Docker, and then it's not that far out. It's just using Docker in daemon mode. It's not that much trickier. So if you have the suitable container, you can just run it, and that's important for accessing it. When it runs as a daemon, we're giving it a name, and then we're saying interactively, as a daemon, remove all artifacts that lie, and we pass one environment variable to MySQL by saying, MySQL, be lenient and allow empty passwords here, because we're just for now working with local files, so there's no security issue. And that really is step 1. So I'm here on a Ubuntu machine, and I have these things set up here, and so I don't have to type and mistype. I just had the command set up for this. So this is the first of the 2. And again, I'm just running Docker, giving the running instance the name TileDB MariaDB, so it runs under that name, with the options that I just showed, including the empty password, and starting that. So that's step 1. The second step then is that we can start an R session inside the Docker container by saying Docker execute interactively again as the user root in the context of the TileDB MariaDB R instance that we had started. And then, if I still have my ducks in a row, should be exactly this command here. So now I'm having R, the current version, the way this was built, and I made no changes to it. That's just how the container is supplied from us. Hold on, and then let me just quickly here. I will just have to, so that was the first command. Second command, now I'm in here, and I'm just going to copy this one. So this is terminal multiplexing. I hope it's not confusing you too much. I just, in the same sort of terminal frame, I have several programs running here by help of something that works on Linux called Tmux and Yobu. So in the container, I just started TileDB, and now I'm just copying and pasting in. Oops, that didn't work. That kills me each and every time. So let me do that explicitly rather than Emacs copy. And now I'm just using, again, my friend fromDataFrame, and I'm saying, let's take the penguins example and just write it to the temp file. Again, this is now the temp file inside the Docker container. Let's keep that in mind. And I just created a TileDB array as we've done all tutorial long. Where it gets more interesting now is that I can, going to copy these commands line by line. We're then bringing up MariaDB. We're also loading dplyr and telling R not to tell us about warnings that come from dplyr and any conflicts. And then the trick is that we're setting up MariaDB via R's database interface package DBI. And one convention for MariaDB and the plugins and extensions is that you want to call the database test. I think that's something that's internally hard-coded. And once you have that, oops, didn't mean to do that, just want to pick this up. It gets actually pretty nice because now we have a connection object which ex ante knows nothing about TileDB. As far as R is concerned, we call DBI and the MariaDB package. So we're having a connection to MariaDB. Using the connection, we can then use standard DBI and Tibble interactions of saying from the connections pointed at where we just wrote a TileDB array, proceed with SQL operations. And now MariaDB will pick up the Tibble expressions, translate them into SQL, send them to MariaDB in the context of a TileDB array, which is pretty nifty. So for example, the first example, and that again just shows the power, is we can just say, okay, from the penguins, just pull me out all the columns that contain lengths in their name. And this is really pretty clever the way it's implemented with DBI, because this query at this point is still lazy. If you do that again, and I like doing it this way too, and feed it into str, you just see two list elements. They're both shallow. This thing really only has the 3 or 5 lines that got printed. It's not the materialized array. It just knows that, okay, we have 2 columns here. Here are the first 2 values. And then it knows, yep, there will be more data. And the way it works in DBI and the DBI database integration with dbplyr is that you call collect to actually manifest your data, and then you really go back and say, yep, get me this. And in that case, it went back and did our usual penguins business, 344 rows, but here we only collected 2 columns, so I have an actual Tibble with the data. And that is pretty powerful, because now we've opened the door to an entire universe of analysis and access functions from the Tileverse, dplyr, Tibble, DBI interface, and all the rest of it. It doesn't know that TileDB is underneath, because that's seamlessly provided by the TileDB plugin for the database backend. And while we are using this here, for ease of deployment just in a Docker container, nothing's stopping you for implementing that on a departmental or group server with the same components. It's just a little bit of setup front load for the AT department. So that's the example that I just showed, the lazy query not materialized, and when we put collect in, the query is fully realized. And at that point, I really have all the power of SQL as provided by our MariaDB via the connection with the plugin. And this is how I set it up. I took this screenshot when I had my screen laid out slightly differently. I since realized that it's better if I work with a larger font here. So now it's just 3 layers, but basically the code here to the left after we launched a container in the background. And here for some reason on the screenshot, so exactly the way I had it set for first. I had one session to write and another session to read, whereas here I glanced over that a little and read from the same that I wrote. But it's really only the file access to that directory that governs that. And my laptop went on to sleep, so I don't see your questions anymore if they're hiding. Yep. William's questions, whether dplyr is query case sensitive. I have no idea. Let me try that. That's, I don't currently work that much day-to-day with SQL, but I remember something that there were tricks, but maybe that's where then SQL differs between implementations, that it can actually be case insensitive with the column names, but I'm not entirely sure. It seems insensitive, so I can also say contain lengths with lowercase l. So good point, good catch. So either, because SQL doesn't care. Yep. So any questions? Actually, we forced all of you to just write them out in the Slack. I guess we also, I can't have my eyes on all of that, but I think the hand raise in the chat would also work. So if something comes up, let us know. Otherwise, I would just leave this example here, having shown the basics, and just basically point back. You can absolutely run this at home if you can run Docker, which, you can run on a Windows laptop, a MacBook, a Linux computer. Docker runs just about anywhere. You just have to Docker pull that container and you're in business, and you don't have to build anything really. And and another trick, and I may come back to that. I'm not quite sure if I have that on the slide now, because the next example is bigger data. So this example I like quite a bit, and that's why I had to quickly jump onto AWS. Because that's something that I did on a bigger machine there. Because we were at some point curious. We have other applications and other problem domains with really large data sets and append to them. And I just wanted to see, am I there yet with the R package and the DataFrame integration? So I just wanted to go out and find a data set that everybody knows and see if I could really go to sort of size with the capital S. And I looked around a little. Many of you may know the package with the example data set. So one step up from Penguins is New York City Flights 13. It's a subset of flight data provided by the FAA to the American public that summarizes all flights in the US during one calendar year, 2013, subject to 3 New York area departure airports. And I thought that's kind of neat. And then I went digging and wanted to find a bit more of that data. It's a little tricky. The R package has a link to a data set that's no longer there. The FAA data set is terrible, but I just kept Googling a little and searching a little. And eventually I found this, and this is pretty good. So the in the PDF slides, when you have them, the link is live. So if I click on this, I think Firefox comes up, but maybe on a different screen than the one that I'm sharing. And it's the same URL that's there, and that maybe spelled out in some other place too. So it's just a top level page with links to the data set under some IBM marketing initiatives where IBM is showing off how much they can do with data. And they basically provide 2 data sets. One is the full FAA reporting from 1987 to 2020. So it really is a much larger span than New York Flights 13 with many more columns. There's a lot of nonsense in there, and 194 million, of course, is unwieldy. But if you just want to get going and test, very handily, they also have a random sample of 2 million. So there's basically 2 files behind this, and I have those 2 files, or started with those 2 files. And then, well, what's next? So it's not bad. The data that IBM curated there for us, and I should go back to the file. I don't think Aaron and I can give you the data directly because it says here somewhere. Is that still on the screenshot or one below. I think the data set is Creative Commons non-commercial. So I guess we can use it, but we're not allowed to redistribute it because or worst case, because we're a commercial entity. But any of you can get to the data this way, and that's what matters. There's two big, so the subset and the full set both come as a tar.gz, and interestingly enough, in the tar.gz is a single really large CSV file that's again compressed. A compressed file inside a tar.gz makes no sense whatsoever, but that's just what they did. So there's a CSV file that's Z-standard compressed, an XZ file in there, and that we can work. And that allows a couple of tricks. My bread and butter data reader is DataTable FRead, and DataTable FRead is fantastic because it can read in parallel and do all these tricks, but it doesn't deal gracefully with compressed files. So to get chunks out, I did something relatively pedestrian, then I just had the compressed CSV file to standard out and use SED to take chunks of rows and then process them. That means that every time I want a chunk, I have to traverse basically the entire CSV file again. If I were to do this more repeatedly, I would probably just expand the file, split the file in different chunks, and then write in parallel from the chunks. But that's not what my example here did, because that was just the first feasibility study to keep it really simple. And similar to many of the examples that we all have seen around tidyverse and dplyr with New York City Flights 13, there are a couple of columns that are interested. We wonder about the year, we wonder about arrival and departure airports, and we wonder about the airline. So that gave me 4 possible index columns where airline, departure, and arrival airports are textual, and the year is a number. So for the 3 textual ones, I already get null domain, so I can always append to it. So I only have to take care of the year variable. And this is not particularly interesting or performing code, but it did the job for me over the space of a couple of hours because the data file is really large, and basically just checks whether the compressed CSV inside of the tarball exists, and then loops over the file and has counter information from where to when, and extracts a certain number of rows from this. It decides to drop a certain number of columns. The data set is very rich because they normalized it in a really, really hard way to be able to fit the CSV formats. When a flight is diverted, there are additional columns that represent from which destination airport they got diverted to another airport. Well, and bad things can happen. Maybe you get diverted again from while you're in a diversion, and from a second diversion to a third. So it goes to a counter of 5. Remember that it covers multiple decades, but many of those columns are just basically empty. So I kind of just said, chuck it, and threw those out. And then I needed one helper function to, in one case, transform a UTF-8 character, a white character, to the normal character. And on a few columns, I transformed bools to ins and made factors into chars. So that's just basically a worker function that I have running over the data that's extracted. And otherwise, I'm just looping. The chunk that I'm currently looking at the URI that I came in with, which I think exactly is an argument here, which basically is a subdirectory where I'm working there, sparse, 4 index columns that I want. And for one of the 4 index columns, the one that's not character, I set a low and high value to allow me to append to it, because I know my data set will not be before the Unix epoch. I can just arbitrarily say, let time commence in 1970, sort of, the hello world standard of time, as well as today, whereas the data really was 1987 to 2020. So I could have also used January 1st, 1987. It's a little sloppy. And then I always just keep track of how many elements I've written. And and I do these things twice. So in this part, I read the first chunk to remember the column names as well, and what initial chunk option I'd given myself. And then for all other chunks, when the array already exists, we'll just take the chunks at that point in the loop traversal, set the column names, and append to the array and keep track of how many we've written. And by the time we've hit 194 million rows, I think I did that in indices of 10 million rows at a time or something like that. And even on AWS on a decent machine, it took a little bit of time, but again, this wasn't written to win a Kaggle competition or be highly performant. I just wanted it to conclude. If I had to do this again, I would split the CSV file into chunks and have a quick and simple R parallel loop to write all the chunks at once, but that wasn't really needed. And once we have that, we can actually go in and hold on, how am I going to do this best? So this is the directory in which I did this, and there are two TileDB arrays, one the airline and one the 2 million DB subset, and create arrays, basically the helper function that I just had there, that I showed in the 2 slides. And I kept the 2 compressed CSV files. This is basically the data that I worked with that came out of the downloads from the IBM site for which I gave the URL. And this, yeah, exactly. This is just the helper that I stored there to download the file and extract the compressed CSV out of it. So hold on, let me, the directory that I'm in, but it's an absolute path, so it would still work. Actually, I think I can pass all of that once. Oops, sorry. And this is now going off against the TileDB backend as driven from the TileDB R package against the 194 million rows, and that took 3 seconds or so, something like that. And that's about as good as we can go immediately, because now I got back basically 776,000 rows, because I said I wanted all the data from the beginning of 2000 to the end of 2000 arbitrary for reporting airline United Airlines. In the beginning, I was a bit more eager and kind of said, yeah, let's look at all the airlines, and just constrained on dates. And the data that comes back is then what I requested, and a chunk for that request is still so large that my R session died because it was more data than I could handle. So this is really big data, so you have to operate it in chunks at a time. And that was a live example on working with really large data. But then we can do additional operations. So we had looked at query conditions earlier. So I can ask a first query condition, all array delays greater or equal than 120, and I think that's minute, which is stored as a float 34. Same thing with departure delays, all greater than 120, I think that's minutes in a float. And 2 initialized query condition objects in the low-level API can be combined by saying first query, second query, and operator end. Let's just see if I can get those over. And then I can fire up that query. And remember, beforehand we had 770,000 rows, but now I'm saying, okay, I just want a particular subset with particular delay properties, and that reduces that one down to 22,000 give or take rows. And once again, that just takes basically no time to get this out of a really large array. And then with the newer helper function that's in the GitHub repo, but not yet at CRAN, we can also write the same thing, basically the same way. Note how I'm cheating here, because this parser will not know that 120 was meant to be encoded as a float because we don't tell it anything about the schema. There's a disconnect between setting the query condition up and the schema at this point because we haven't connected yet with an array. So it would set this up as int, and then the query doesn't actually compute down because we don't have a, which we probably should add, we don't have a simple and smooth cast to go from an int to a float. You have to really have the right type in there. But if you do it with that way, with the by essentially implicitly forcing a float by having a floating point expression in the query, you get the same thing operating, but because numerically, of course, it's not exactly the same. And that may have to do with how analysts at the FAA wrote down the records. It's actually 400 data points less than if we're doing hard 420.0, which, you know, makes some sense. And yeah, that's what we can do with the flights data set directly from an R prompt. But another thing, of course, that one can do, yeah, this is what I just showed, and the little lingo, little detailing on you know, making sure it gets picked up as a float. And yeah, this is sort of fully remote, even though in a sense it's a local file system. We only get the slices of data back that we're requesting. So I could have done this over cloud storage if the array was in an accessible bucket, which right now it isn't. It just sits on AWS, basically in a machine. We're getting efficiently 22,000 rows out of 194 million. But one thing that I quite like too is to use one additional option for Docker. If we say, let's mount the Docker container in a particular directory, outside directory where we are, in pwd in the bash shell is current working directory, it will accessible on the inside under /mount. We can then do the exact same thing of spawning MariaDB and R and saying, you know, let's start MariaDB, let's start dplyr, open a connection to DB, to MariaDB exactly as I've done it on my machine locally, but have the Tibble DBI connection object go to the mounted directory, which then inside the running Docker connects it to the outer file system, and I get the outer airline that we'd written before. And then we get the same thing on 194 million rows via the dplyr logic. That will just take me a second to copy and paste this out, but not too long, and I think it's worth it. So let's just, and that was one of the reasons I had 2 sessions here, so maybe let's do that on the left-hand side. And again, it didn't copy. All right, so that ran. And then this one we'll just restart. Oops. Restart inside the container is really what I wanted. And the key here is this -v argument for bind mounting an outer directory to an inner directory. Again, it's R inside the Docker container. And so let me now I just rearranged the layout, so that was just a little trick there. So now we've started this. Set up a DBI connection to database test to get access to a MariaDB extension, in this case the TileDB one, which it'll resolve, I think, by finding the directory, and then oh, Oh, sorry, my bad. Yep. I did this, I pivoted back because the screen was constrained before I rearranged it inadvertently and started that from the wrong subdirectory. But actually I can save myself that way. I don't actually need to restart it. Hold on, let's just do it here. In the Docker container, there we go. In the Docker container, start these two. Get a connection object, but then instead of mount airline, because it's not in a working directory, I need to just expand that. Mount is where we started it, and then it's git, and it's TileDB flights. And there we go. I get a lazy query back, and it immediately comes back by, I guess, just querying the schema information and getting, a limits 10 back of 1, 2, 3, 4, 5, 6, 7 columns that all match this selection criteria. Again, I was cheaply doing something having depends in there. But now I have TileDB via SQL on an ad hoc array that I've written with 194 million rows from a CSV file, which I can directly access in TileDB via R or via the MariaDB extension.
Dirk, do you have thoughts on the pros and cons of querying directly with R versus through the our MariaDB interface?
I would say it's probably driven by different use cases. When the analysis that you want to perform naturally maps and you're fluent with all of the dplyr verbs and alphabets, then going via MariaDB is very appealing because your immediate work with dplyr. I looked into doing what a couple of other packages have done and taking expressions and translating them directly into something DBI resolvable on top of an array. And it actually turns out that that is a metric ton of work. It's probably as much work as we have in the package because just, remember how I did selected ranges to select by rows and what have you. We basically have to pick up, filter, select, mutate operators, bring out the operations that they're doing and then re-implementing them straight on top of the TileDB arrays. And I was a little fearful that that not only might be a lot of work, but also a venue for possible infelicities and bugs. And I figured as a first proof of concept, it's much easier for us to rely on what's implemented, tested, and widely used, and just go to dplyr via DBI and that interface. The main constraint is that the deployment is a little harder because you have to have a MariaDB build with the TileDB extension there, but it's not insurmountable. And I would expect that there's a small amount of performance to pay because you have MariaDB in the queue, but most of these things happen effectively with zero copy where possible. So I wouldn't expect it to be a deal breaker. And can you query data present in MariaDB together with the TileDB dataset? No, the trick here really is not quite that you get, well, what are we really doing? We're using MariaDB to access data stored in the TileDB array via the TileDB extension to MariaDB. So that means you can get TileDB data via MariaDB. You can't use this to get non-TileDB data from MariaDB, but you get non-TileDB data from MariaDB anyhow. So maybe that wasn't directly your question. So maybe you can rephrase and then we'll revisit that. As for as for Elizabeth's follow-up question, so basically an expression such as this one, Aaron, can you not? If I highlight on the screen, you see the highlight line, right? Oh, yeah, perfect. It's always a bit unclear whether the cursor follows. Now we're in a deployer pipeline, and I could have 10 more verbs in here. But the key is they actually get resolved by going via DBI, because it knows that this con object is a DBI table object. So it translates it into SQL. And we'll get this by having the MariaDB SQL engine resolve it for data that happens to be stored in TileDB arrays. So it's the combination of both of these, and you need them that way. We don't have a SQL query engine inside of TileDB, so the only way to get to SQL commands right now is via the MariaDB extension. I hope that that answers that. Okay, great. That was what I had on the really large data and the flights example. So with that, let me while I'm here, maybe just do one piece of housekeeping so that I don't forget that. So we started a Docker in the there we go, so that one's gone. So I can log off here. And log off there as well. Great. Back to the next example, a little bit of geospatial stuff. So LiDAR, light detection and ranging, quite popular these days in a variety of fields, lots of spatial analysis. We have some really performing R packages, LiDAR, LiDAR, don't know quite how it's pronounced by Jean Romain, who is motivated by forestry examples. There's a lot of talk, of course, for LiDAR, helping with autonomous driving, for using LiDAR as opposed to full image resolution. And there are a great many public data sets as LAS or compressed LEZ files. And because these are multidimensional arrays, they map really well to TileDB. One thing that we have to do, though, is we need a reader for LAS files. And one good way is to go with the point data abstraction library, PDAL, which can be built in such a way that it knows LAS and a lot of other spatial data formats, as well as the TileDB extension. So here again, there's a Docker container, TileDB Geospatial, in which PDAL, which has, not unlike MariaDB with its extensions, the ability to be built in a large number of different configurations, and we added the TileDB configuration to it. And you're driving a conversion of LAS or LEZ files with PDAL by giving a JSON control file. So this is just a little array with 2 entries, and you say, okay, we want the LAS reader. So we're taking in a LAS or LAS compressed file, in this case, file name outzen LAS, and we're writing from PDAL with the TileDB option to the outzen TileDB array with a particular chunk size and large chunks. Then you can, and all that is described pretty well on the TileDB website for geospatial. And I did pretty much the same, just invoking it from from the Docker container, pointing at the this particular file. That's a demo file that has been used in a couple of other demo locations, and it's actually stored at the PDAL GitHub repository. And oh yeah, actually, sorry, these slides showed that how I set this up. So I just did this from R, but basically just wrapping R around shell scripting. I want this particular last file, which I can get from geospatial research group site at the University of Illinois. It's a particular Cook County where I live. Last file, and we'll visualize it in a second, and I think you'll recognize what subset that I'll use. And if the file isn't present, This is just a little bit of conditional R, set the options to a large timeout and slurp these 450 megabytes in. And I've already done that and created the array so that we don't have to do this live. Goes in, in the background for the tutorial and this soft link. So the file is there, so we would basically skip over that. Similarly, if the TileDB array top-level directory does not exist, it means we have to invoke Docker to create it. And this is similar to the previous example. We're running Docker. Here I'm using another option I hadn't used before, and I make sure it runs on the same user ID I have on this Ubuntu machine so that I have the same file permissions on it. We're using the vs flag for mounting again from the current working directory and writing into inside Docker container mount point data, and then telling Docker to start in data. And that just means that its process that it starts with this command will have all this stuff local. So pipeline JSON that I set up where the file was local and the output array was local is all in this directory. And then all you really have to do is run that. And that doesn't take very long. This takes a couple of minutes because it's 450 megs. And once that has happened, you have the file in a local directory, just as I have here. And you can reproduce the same analysis at your end the exact same way. So with that, I can now hop in and go to the code after the conditional writing. And so now, again, TileDB is loaded. And I this one directory reindexion. Yes, let me try that again. Now I'm in the right place. And so LiDAR is geospatial, often coordinates X and Y on the ground and Z a height, as well as what the laser results get back, often color coordinates, what have you. So here I'm just requesting a particular chunk from that LiDAR data set. Forgotten how large it is, all rows in those 450 megabytes. But basically here I'm having 108,000 rows over 15 columns. And we just got that out of a TileDB array. But one of the workhorse packages for working with LiDAR data is the LiDAR package, which I quite like. It seems to have a slight disagreement with the PDAL library in front-end package over one particular columns, which we always need to cast to integer before we give it to functions from the LiDAR package. But then I can create a LAS object from the array that I'd read. So I've read the TileDB array back in and fed what was L, 15 columns, into the LiDAR package, and I wasn't very creative with my names here, and just called this LL for the LiDAR L array. But now we're in the realm of the LiDAR package, and it has a default plot method, which then, because it's LiDAR data and it's geospatial and you want to flip around it, lets you zoom this, and the subset that I found from this particular tile of LLS data is what used to be known as the CS tower and is now the Willis tower. And the LiDAR measurements that come back, I guess, just scattershot particular heights and haven't yet filled in. So this is all, whatever it was, 108 stories of the Willis tower. And that's one of the two plotters. That one sort of runs by default when you install the LiDAR package. There's another one that I quite like, which I found there was a reference to it on the GitHub repo of that package. Its author in Quebec has written basically reutilizing the RGL package, a faster and lighter plotter. You didn't see the improved access to the plotting device right there because the subset that I've chosen is relatively small. But what he's doing here is notice the message, point cloud killer must be closed before to run other R code. When we plot with RGL, we take the R vectors and actually transform them to other data structures, make copies, rearrange them, allocate, what have you, before we pass them to OpenGL for the plotting. That takes a moment. This one's more clever and just passes the R data straight through, but that means that, we're now paused in execution while this viewer is running. And that one's on GitHub in a repo LiDAR viewer, but I quite like it because it's lighter weight. And that commented out line works for me on my machine because I installed LiDAR viewer from GitHub. It may not work on yours until you install that package. That was that example. And then we have real quick, one more that connects me back to what I used to work on for many, many years, which is financial data, mostly from exchanges, which are often timestamped. These days, very high resolution timestamped, which makes it challenging to get good example data because selling data is a major source of revenue for the exchanges. So what I found here is in a registry of open, freely available data sets. I'm sorry, I flipped that. But, this was the one that was non-commercial. So I think the earlier data set from IBM over the flights, of course, that's US government data. We could have redistributed that. So everybody has access to that because that's done on US tax dollars. Open use license. This is the one with non-commercial. And they have some immediate language in here that I quoted because that's just how exchanges tick. If you want higher resolution data, please talk to us and we'll charge you. So what we have here is real data from the exchange and it grows and they update it every hour, but it's a little boring in that it is minute bars rather than really high frequency transactional data. But still, it's not so bad. So when I first looked into that last fall, I downloaded a few data files and I still left it at those. So for a really simple and quick example, I again append multiple CSV files into one common array for which I just have to pick up column names and indices and the array description, the creation in the first pass, and in all other paths I just append. This really just is a helper that collates two date and time columns into a datetime object and then drops them and doesn't do much more and turns it into a data table object. And here in the writing step on the first step in the loop, we create, and in all others, we just append. And that's pretty straightforward. And once you've downloaded a bit of data, that can run relatively quickly. And once you have that, and that example I will show you. And for that, I have to remember what directory they're in. I think I have that in the code example. Yep. So we need TileDB, the table, and this particular array sits for me in a one-off repo that I worked on that. So this is the list of files that I injected. It's just 9 or so of them from last November. This would be the worker function to inject them, but we've done that. So I will just do one quick example of reading that in. So we open the URI as a data frame, and now we can, for example, show how we would get time series data frames out of a large array. So here, it's a European exchange in Frankfurt. One of the securities listed there is the car manufacturer BMW. As a consumer brand, everybody's familiar with them. And here I just say, okay, just give me BMW, no other company, and give me an hour's worth on November the 4th. Isn't a particularly impressive day. That just happens to be a recent day when I downloaded it. And then in order to plot this, I use a helper package called RTS. I always forget what R is for, and it's just a not that well-known package. And you can set layouts easily to combine plots. So it's an hour's worth, so we get 60-minute bars. And then below that, we get a volume bar. And voila, that's the data set what we got from there, because it's actually stored as volume bars, so plotting bars in a financial structure. Just seeing the question now from Kim. Yeah, no, absolutely. So so the LiDAR package, for example, by Jean Romain, works with multiple files, and then you index the different files and combine them. We wouldn't do that. We write everything in a really large array and just index by X, Y, and Z. And if you wish, even time, because you could have LiDAR measurements from pre-harvest, mid-harvest, post-harvest, and whatever, and index by different dimensions. So that makes it actually really, really rich, because you don't have this soup of having to deal with, large n number of files and picking up the right ones. It's all in the index, and TileDB accesses this for you. So that's actually a good key example of why this works so well. Same here. If you look at the website at Amazon, the Open Registry, each hourly snapshot, oh, you saw it in my directory too, but in each hourly snapshot is one CSV file. So if you want multiple, you just have to find the right files and what have you. You just write them all into one large array and index by time. It's much better. And that's the example that I just showed on one slide. And that brings me to the end of what I had, and we should probably pause a little. Aaron, you're muted? You're unmuted? Yeah, so 5 minutes?
Sure. Should we take another 10-minute break?
Yeah, that works. I will be here, and I will, now that I no longer have to talk and make a mess with my slides and code examples, I will monitor the Slack like a hawk and try to answer questions there while Aaron gets ready, and then watch the chat for him while he presents. All good? Just unmute for a second. So Aaron and I were just checking notes over the SQL intersection question and whether we picked that up rightly. I think we finally realized by shooting back and forth and not being quite clear what the question was, the question really is, can you have a SQL query that goes back against TileDB content as well as other content that MariaDB may be set up to query? And the answer to that is yes, absolutely. Because that's the beauty of a SQL execution engine. You fire a SQL query up and it resolves the query. And if the table that it wants to go to happens to be TileDB data, and reads it via the plugin in this build. And if there are any others, normal database or other database tables, it will read those. And then, join, union, whatever, do what the query is as a database engine does. So that would work.
Had a bit of a Zoom glitch there. Okay, so for the last demo today, we're going to look at a more biological use case. And I'm going to walk through the process of using TileDB to store results from a large collection of genome-wide association studies, which are called GWASs for short. And no problem if you have never heard of a GWAS. I'm going to give you a high-level overview just for some context. You don't need to be a genetics expert or anything. All you really need to know is each individual GWAS produces millions of summary statistics, and we want to store them in a way that makes those statistics easily accessible for downstream analysis. So the goal here is to provide kind of a more in-depth example that requires some consideration for how best to store our data in TileDB. So we're going to examine some of those considerations for this GWAS database that we want to create through this tutorial. So just a little bit of background to get everyone on the same page. At the highest level, a GWAS just allows you to identify regions of the genome that are associated with a particular trait. Oh, and I just realized I'm not sharing my screen, am I, Dirk?
I was just about to point that out to you.
Thank you. There we go. Now, hopefully everyone can see that. Cool. Okay. So yeah, GWASs let you look for regions of the genome associated with the trait. So traits could be anything: hair color, risk for alcoholism, or the risk for developing a particular type of cancer. And the way you perform a GWAS is you need to sequence the genomes of a large population of individuals, so you can identify the genetic variants in each person. Variants being just the DNA sequences in a particular spot that differ from what's typically observed at that location. So 95% of people might have an A, you have a G. And we're all carrying around millions of variants, which is what makes us all unique. So the question you answer with a GWAS is which of those variants influence a trait of interest. So kind of a fun example that was performed by 23andMe a couple of years ago is, are there any genomic regions associated with preference for strawberry ice cream? So the way you carry this out is you ask 1,000 people if strawberry is their favorite flavor of ice cream, yes or no. Then you examine each variant site individually and perform an association test that determines whether more people with a particular variant said yes than you would expect by chance. So here's what GWAS results look like typically. So each row here is a different variant, and the identifier in the first column tells you where in the genome that variant is located. So the variant in row 1 is located on chromosome 1 at the 15,791st position. And then we have these 2 letters here. Those are the sequences, the 2 possible sequences of the location, C being the more common one, T being the alternative variant. And then we have our summary statistics for the association test. So we have a beta value, which is the estimate of the effect. We have a T statistic and a standard error for the beta values, as well as a P value, which gives you the significance of the effect. So this is what the files will look like that we're going to ingest into our array. And the data we're working with comes from the UK Biobank, which is a incredible effort in the United Kingdom that has sequenced hundreds of thousands of individuals and collected all kinds of data about them. So they have survey data, medical imaging data, you name it. So it's an incredibly rich resource for biomedical researchers in a massive data set. And they have leveraged this data to perform GWAS studies for thousands and thousands of different traits, the results of which are all publicly available. So you can browse the full set of results in a Google spreadsheet that I have linked at the end of this section. And for each GWAS they performed, there's a compressed TSV file available with the results. Each of these files contains about 10 million rows, and they're usually about 500 megs compressed. Okay, so for the goals we are trying to accomplish for this is we want to take all this data and put it into a TileDB array so the results can be sliced directly without having to download the files first. Especially if you want to do something like make comparisons across traits, that would mean you'd have to download all of those files before you could do any kind of analysis. And we want to query the data by genomic region. So if I'm interested in a particular gene, I can easily slice all of the variants located within that gene's region. And then finally, it'd be nice if we could query traits directly by their descriptive names so we don't have to perform a separate join with a lookup table, for example. Okay, so let's get started. So if you want to follow along live, you can use this snippet to create a copy of the tutorial script in your local directory. One of the first things we do in the script is use the download GWAS files helper function to download the GWAS files. So this is part of that same package Dirk was showing you earlier. And that will download 6 different files that have all been slimmed down for this tutorial just to keep it light and fast. So each one is only about 15 megs. So if you do want to follow along, they shouldn't take too long to download. So the files, like I said, they're slimmed down. They only have a subset of all of the chromosomes. Another change I made was to parse out the genomic positioning information from these variant IDs. So in the files you get, there's going to be these 4 separate columns, which is just information I extracted here. And the reason is I want to use this information to create an array that's sliceable by the chromosome and chromosome position. So we needed to separate those out into separate columns. So this is a diagram of how we are going to model this data. So we're going to create an array with one dimension for the chromosomes and then one dimension for chromosomal position. And with that layout, you can perform a typical R-style query and index by a row and column name, which will retrieve the corresponding cell. So for example, if this was chromosome, this is chromosome 3, this is the, I don't know, 5th position, that would grab this cell here, which would contain all of the relevant information for that specific variant. So all of those summary statistics, which are stored in separate attributes in our TileDB array. And then we'll add a third dimension for the multiple GWAS analyses. So this is going to be a 3-dimensional array, and that third dimension will be for all of the individual studies that were performed by the UK Biobank. So that's going to let us efficiently grab specific regions for specific traits that we can pull into R and visualize or perform any of the other kind of statistical things you'd want to do in R. So these are the final dimensions. And remember, when you're designing an array, the dimension order is important. We're using phenotype as the first dimension because in our use case, we are typically querying for GWAS specific results for a particular trait. So selecting one specific trait will automatically filter out the vast majority of the results, so TileDB can quickly zero in on the relevant slice of the array. So I'm going to switch over to R so we can look at the code and start building this. So this is the example script that's included with the TileDB useR 2021 package. And again, it's there if you want to follow along later, if you don't want to go ahead and do it live. But we'll load a couple of the packages we need here. The data directory is where I'm going to download those GWAS result files. And then this is the location where I'm going to create the array. This is just some housekeeping stuff. We're going to make some ggplots. So I set up a theme that makes it look a little nicer. So run this to download the files. I have already downloaded them here, so I don't need to do that. So on to creating the array. So the first thing we need to do is create the dimensions. So our first dimension is for the GWAS phenotypes. So we want to be able to query by the names of these traits. So we're going to set the data type to ASCII in order to create a string dimension. The second dimension will be chromosome, which is also going to use strings to accommodate the non-numeric chromosomes, X and Y. And then the third dimension is chromosome position. So these are denoted by positive integers. So we will store them as uint 32s. And then I'm limiting the domain to the size of the largest chromosome, just as kind of a safety check here. So if you're trying to ingest something that goes beyond 250 million, there's probably a problem with your data. So created that, and then we combined our 3 dimensions into a single domain for the array. And here, this is where we're specifying that the order of the dimensions. So we want it to be phenotype, chromosome, position. Okay, so next step will be the attributes. So the attributes are going to be all the remaining columns in those results files that we're not using as dimensions. Really, there's 2 categories of those. We have 2 character vectors or 2 character columns for the 2 alleles, the reference and alternative allele. We're storing those as chars. So those will come back to us as characters in R. And then the summary statistics are all stored as doubles. So we're storing those as float 64s in our TileDB array. And as far as compression, TileDB has a wide array of choices for compressing your data, and it's very often worth experimenting to optimize and find a good balance between performance and storage. So here I'm just using Z standard for everything because it does provide a good balance between the two and generally works pretty well. But if you're creating a massive array with a new schema, it's worth trying some different compression options to see how it affects your results. So we did that, and then we tie the dimensions and the attributes into our schema. I am going to use the allow duplicates flag because there are cases where different variants will share the same genomic start position, and we want to ingest both of those into the array. So we create our schema, and then we create the array. So I usually include this little snippet here in my scripts, which basically just checks to see if there's an array already at the location that I want to create it at. And if there is an array, it deletes it. Now, be careful with this. If you have large arrays that took a very long time to create, you probably don't want to do this, but it's handy for experimenting, and it's nice because it uses TileDB's virtual file system functionality. So this works whether or not the array is local or remote on S3. And I think I already have an array, so I will delete it. So then we just run TileDB array create. That should create our new empty array. We can verify here. Yep, so it's called UK Biobank GWAS DB. If we look inside, there are no fragments written yet. So now we're going to ingest the actual results, so the data into the array. So the first thing we need to do is open it back in write mode, which I will do here. And then if we print that out, we get the nice summary information that tells us where the array is. It's a sparse array, etc. And for the actual ingestion, I am just going to loop through each file, which we've identified here. So this is our vector of the 6 GWAS results files we downloaded. And here is where the ingestion actually happens. So we're going to loop through each one. I'm going to use the vroom package to load it into R, which is great for loading in large tabular data. And then here we're actually performing the ingestion. So I will run that, and it's going to go through each of those files one by one. And here we're doing this all locally and serially because the files are very small, so it's not a big deal. But this approach wouldn't work if we were trying to store, the entire UK biobank data set, for example. But as Dirk mentioned earlier, TileDB supports fully parallel reads and writes. So we could have easily performed this in parallel. So if you're at an institute with access to an HPC, for example, you could have dispatched batches of files to separate nodes. It could all be written to the array simultaneously. We also offer a service, TileDB Cloud, that provides serverless infrastructure. So using that, you could actually spin up as many nodes as you need on demand and ingest all of the results files simultaneously. Oops, forgot we actually should have a slide. Let's see, did I refresh these? No, I don't think I don't have my slide here. Well, it's okay. So we have a functionality on TileDB Cloud that lets you write user-defined functions. So any arbitrary task can be defined as a UDF, and then you can run those in task graphs, which can be distributed across as many serverless nodes as you need. So later on, I'm going to show the full array I created with the UK Biobank data set, and that was ingested using our TileDB Cloud UDX. But for this little one, fine to just do it serially as we did here. So that's finished. To actually query the array, we need to reopen it in read mode. I'm indicating that I want the results to come back as a data frame. And then these are the specific attributes I want to retrieve from the array. So we're going to look at a couple of different types of queries we can perform with this array. So the first one is just a simple R-style array where we're using square bracket indexing to subset by row and by column. So we're going to index the array to pull out just the GWAS results for water intake, which is one of the phenotypes they looked at, and limit it by chromosome 20. And then I'm wrapping it in a tibble here just so we can print the results out nicely. So we'll print those out, and you can see there's our dimension for phenotype, our dimension for chromosome, and then we have the third dimension, which we didn't limit, so it's returning all of the results in that chromosome. And this data might be easier to visualize. So here we returned, let me get my zoom face out of the way. We returned 290,000 variants from that chromosome. Here we're looking at the negative log 10 transform of the p-value, so we can kind of spread out those lower p-values. This is called a Manhattan plot, which is typically how you visualize the GWAS results. So if I want to query on all three dimensions, I'm going to use the selected ranges approach that Dirk showed us earlier. Basically, we create a list with an element for each of our dimensions and provide a query range that we want to limit to. So I'm doing the same thing. I am pulling out results for water intake on chromosome 20, but now I'm adding a range to limit the results from the chromosome position. So we're just going to pull out the variants that are located between 5 and 6 million base pairs. So I attach that to the selected range slot, re-query the array, and then we'll just update our plot. So the x-axis is the same, but you can see we've just pulled out now those points for that specific region of the chromosome. So the other kind of query we mentioned we'd like to perform is looking at results for the same region, but across phenotypes. So maybe you have GWAS results for, chocolate ice cream preference and strawberry ice cream preference. You want to see how those results differ. So we can run the exact same query, but now I'm going to set the phenotype dimension to null, indicating I want all the phenotypes back for just this region of chromosome 20. So update the selected regions, rerun it. I'm going to create the same plot, but now we're faceting by the phenotype dimension. So you can see for all 6 of the phenotypes that were ingested into this array, we've pulled out the variants for that same region between 5 and 6 million base pairs. So I'm going to pause there for a second to see if there are any questions we need to get to. Why is there a gap in the middle of the Manhattan plot? That's a good question. Oh, did someone answer it? So that's the centromere. Exactly right. So that's sort of the middle of the chromosome. If you've ever seen a picture, they kind of look like bow ties with a weird circle in the middle. So those are regions that are full of highly repetitive sequences. Generally, there aren't a lot of gene coding regions there. They're also difficult to sequence because of all the repeats. So usually you just don't have data for that part of the chromosome. But good observation.
Can you take the one preceding it? That was too domain specific for me.
Which was that? If a cell...
Yep.
If a cell indexed by chromosome number and chromosome position represents more than one variant, the data for each variant would be contained as multiple sets of attributes in that cell. Yeah, so you would, if we were querying it as a data frame, you would just get back multiple rows for that cell, which would normally just be a single row. So this is a case that crops up pretty often for our VCF product. So we have a program called TileDB VCF for variant call data. So that's data that's ingested directly from VCF files. And very often you get different variants that share one position. And when you query the array, they just come back as multiple rows in your results. Okay, so if there's nothing else, I will get to the last section. Which I guess I don't have the slides for, unfortunately. Okay, so that's fine. So if you did follow along and you created an array on your local machine, we developed a small Shiny app that lets you explore the array. And unfortunately, it's not in the slides, but you can install it yourself here. I'll just paste this into Slack so everyone has it. So if you install that and just load it and run the app, then you should be able to paste in the local file path for the array you created. So in my case, it was this. So I'll paste this in. You need to load the array. Let's see. Right. And then if everything went okay, you should get a green box here, which indicates that it is a valid array and it was loaded into memory. So what you can do with this app is once it's loaded, it allows you to query it, interactively without having to worry about the R syntax for now. So you can specify your phenotype of interest, which chromosome you want to look at, then hit submit query, and it basically is performing the same kind of queries we were just performing earlier. It will also generate plots for you. And then we can also look at statistics that TileDB optionally provides. You have to enable the statistics. I think the function is TileDB _stats enable in the R package. So, performance is, of course, paramount to TileDB. So we track every part of the stack and provide pretty comprehensive information about how much time was spent in each place in the code. So, most critically here, we can see how long it took to read the array. So that's the sum of the read time. If anything feels slow, you can kind of go through here to see if anything looks off. So it's very useful for diagnosing performance issues if they should crop up. And the last thing you can do here is this will actually generate snippets, so you can perform the same query directly in R or in Python, because of course we are a multi-language format. So this is really just meant to kind of help you verify your local array was created successfully and provide some hints for exploring it without worrying too much about the syntax. So we've been working with this sort of toy version of the data set for demonstration purposes, but we also did ingest a much larger swath of the full results to an array on S3 that everyone who attends this tutorial has access to. And if I reload the array, it should fill that in by default. Right, so here it is. So this is the URI for that array. So I can load this one, and now everything is happening remotely. So this is like a 200 gig array that's on S3. And it would help if I ran my query first. We could perform the exact same queries we were performing with with the smaller one, we'll get the plots back, the results. You can move it along and query a different region. And, of course, this is all remote, so the normal caveats apply. Performance is going to depend on the speed and reliability of your connection. But generally, the performance is very good. It should only take 1 or 2 seconds at most to pull back tens of thousands of these variants. And 200 gigs, while it's fairly large, it's not massive. We have other genomic data sets on TileDB Cloud, for instance, that are multiple terabytes in size, specifically for VCF data. And, that's a case where we have customers actually using it in production, so it's been highly optimized. But if you do any kind of sequencing or VCF work, highly recommend checking out some of our notebooks and exploring those data sets. So that's all I have for the GWAS use case. Let me see if there are any final questions about it. Yes, the Shiny app is available online. It's hosted on shinyapps.io. I have the lowest tier paid account, so I think I get, 25 hours or 50 hours or something like that. So if it shuts down, it's because I ran out of hours, but you can install it and run it locally as well. Yes, so someone was asking about sort of the pre-processing for the data used in the analyses. Yes, this data comes from the UK Biobank, so it's really pretty homogeneous since it's mostly people of British ancestry, but they do have very detailed methods about correcting for population structure. So that's all I have for the GWAS use case. Dirk, do you want to take it home?
So yeah, thanks for Aaron. That was really nice. In summary, what Aaron and I tried to show you and convince you of is that TileDB is an open source embeddable storage engine. The underlying C++ code is all MIT licensed, will always remain open source, can never be taken away from you. Similarly, that provides the access layer with which you can store any type of data in this open source format. And we believe strongly that an implementation to accessing it is a really rich and really feature-rich and capable approach of accessing this. Native to this format is a full cloud operation on the 3 leading providers. We work a lot with AWS, just as everybody else does, but it works the same way with Google Cloud Storage, and a few bioinformatics projects work with that, as well as with Azure. And we have a couple of clients in more Microsoft-centric environments who are on Azure. The nice thing with all these cloud backends really is that it's limitless scalability, because it's no longer your machines, it's their machines. You can just fire them up, and you can bring that in-house to the same way. We illustrated time travel and encryption. All of that is provided on top of the generic C++ API that Python and other languages access via the R package. Also MIT licensed on CRAN, will never be closed source and always be open source there, to be used and extended by all of us, really. And there's already a bioconductor package, TileDB Array, it's called, without a hyphen in there, that uses in the context of some of their higher level data structures. We're aiming for high level R-friendly interfaces that we've seen from DataFrame, TileDB Array, and others, as well as lower level access. We showed some short examples, and Aaron went over that with the GWAS example. And it's also fully interoperable with DBI and Arrow as illustrated. We really think that multidimensional sparse array can store just about any type of data for you, straight up numeric data, VCF arrays, data frames of various types. We covered a few of those, including geospatial, financial, and genome-wide dispersion study data. But the sky really is the limit, and we'd love to be in touch and help. So just contact us, and some of the contact informations will come on a slide in just a minute. Further resources that are there this was an excellent post that Stavros, our founder, wrote last fall. I had come across basically not a formal request for comment, but sort of a laundry list of nice requirements posted by the OpenML team. That's a bunch of, as I see it, I think mostly European folks interested in machine learning. And they were musing about what requirements scientific open data structure would have. They went a particular way, but we wrote this blog post and basically addressed every single one of the requirements that they have and showed how it maps to TileDB. So it's a really nice, detailed, thorough, but not too long description of the capabilities of TileDB if you're coming from a scientific data angle, which maps to enough business cases too. We've got websites. docs.tiledb.com just illustrates everything. There's lots and lots of sub-levels to the navigation on the left of that screenshot. We added the two main GitHub repos here. The R package has a package down documentation site as well that's linked from the repo. And you can talk to us by email, hello@tiledb.com, and a friendly colleague of ours or we will be back in touch. The web address, the docs that I showed, there's an online forum for feature requests and support. GitHub I showed. We are on Twitter. There is also a community Slack that we set up a couple of weeks ago and which is just slowly getting going. It didn't quite go from 0 to 100 as the one here for use are when the other online forum didn't quite stand up to the charge of all the users. But if you hit that URL or the one at the bottom of our homepage, you can join the Slack and ask any questions there. And, we're happy and chipper and hiring and growing. When I came here, we were still single digits employees. Aaron came a little later and it was no teens, and we're now in the 30s. And I'm sure that'll continue that way. So if you're interested in this and have some skills to make the product even more awesome, just talk to us. And with that, I'm amazed we're only just about 2 minutes over. So that should just be it. And I believe that Sydney and the organizers now want us to stop really soon because the overall time budget is a little limited. So we'll probably have to stop the recording in just a moment. And I think that's just it. But we'll be monitoring the channel while user is still ongoing. That Slack then may die out. I'm not quite sure what's happening, but there's our community Slack and all the other efforts. You have the GitHub repo with the code that we looked at, and we may have missed one file update or two. So file an issue ticket and keep us on that. But otherwise, thanks for all the really excellent feedback and questions. It's been a pleasure, and I hope you found TileDB interesting.